and my mouse moving, hopefully.
Yes, yes.
Yeah, okay, perfect. Good. All right, great. So yeah, so let me begin. So thanks a lot to the organizers. It's been a great conference so far. Thanks a lot for the opportunity to present this work. So as you can see, I'm going to be telling you about measuring temperature. And this is, of course, a very important problem for kind of all kinds of different applications in quantum technology. So, for example, in quantum simulators, we typically want to know what is the temperature so that we can either calibrate the simulation or so that we can kind of measure some interesting thermodynamic properties. There's many other applications, of course. So, I mean, the problem with this is that in general, measuring the temperature of a very cold quantum many-body system is difficult. Okay, if we try and just do it by directly measuring some observables, because for a generic system where we can't solve the Hamiltonian, we don't actually know how to connect local observables to the temperature. Okay, and so the classic solution to this, used for hundreds and hundreds of years, is to introduce some small probe system that we understand very well. So you can think of a bit of mercury in a glass tube, or in the quantum regime, some few level system that we understand very well its level structure. And then by measuring this probe, we can kind of indirectly infer the temperature. And so this idea in the quantum regime has been explored quite a lot over recent years, including by sort of many interesting works by people in the audience. There's a very nice review by these guys, and I think we're going to hear from Luis Correa in much more detail about this problem later on in this conference. But one of the main kind of assumptions underlying most of these works is that the system that we want to measure is always in this kind of canonical ensemble, right? But this actually is not necessarily that good of a description for these kind of really isolated quantum simulators that I mentioned. So here you really have something like the extreme limit of an isolated system described by a pure quantum state undergoing unitary evolution, but nevertheless we can see the kind of emergence of thermal behavior in these closed systems. And so the idea of this talk is to try and see how we can measure the temperature of these really pure quantum states, and can we do it in a kind of fully quantum mechanical way. Okay. All right. So to explain what I mean, let me kind of take you back to a very foundational experiment in the history of thermodynamics, which is this famous paddle bucket of James Joule. So Joule was trying to measure what he called the mechanical equivalent of heat. So he wanted to basically measure how much work translated into a given temperature change of some kind of thermalizing system. So the key ingredients of this experiment are he had some sort of water, some other fluid in an isolated container, so a really good thermal isolation, some controlled forcing, which here corresponds to kind of rotating some paddles and doing some work, okay? And then the final ingredient is this in situ thermometry to read out the temperature change, okay? And this is a diagram taken from Joule's original paper, and you can see the thermometer goes here, okay? All right, so what's the kind of quantum analog of this paddle bucket, right? So now let's imagine that we really have this extreme limit of an isolated system, for example, some ultra cold atomic gas prepared close to its ground state, okay? And this is a system that's going to be in a pure state through the entire evolution. It's fully thermally isolated, right? And we know this very well in these experiments. So then we do some controlled forcing. For example, we might shake the trap potential or something, and then leave the system to evolve. And because of the interactions between the particles, after some time, we're going to have some kind of emerging temperature. And then the question that I'm going to kind of describe is how can we measure this temperature in situ with a quantum probe, okay? But first, let me explain a little bit more about this thermalization, okay? So this slide basically details a computational experiment that we did, some numerical simulations of a particular model. I'll kind of there's a lot of information here, so I'll take you through each kind of figure in turn. Okay, so the system that we consider is this Hamiltonian here. So this is just describing a one-dimensional chain of spin half particles. So this part here is the famous XXZ Hamiltonian, where you have some kind of kinetic energy term given here, and then this is some kind of interaction energy between kind of neighboring spins with the same orientation, okay? And then this is a staggered magnetic field, which is basically breaking the integrability of the model, okay? And this is crucial to allow for thermalization, all right? So So let's imagine that we start our system, okay, in its ground state, right? And then we drive it with some kind of local oscillatory field, like so, okay? And what's going to happen is the system is going to absorb energy steadily over time. So this is showing the average energy as a function of time. And so if I allow the system to kind of absorb energy up to this point here, and then I switch off the drive, then I've prepared some kind of highly non-equilibrium pure state of this system. And this plot here is showing you the energy distribution of this state, okay? And you can see that it has these kind of this very structured distribution. You have these peaks separated by multiples of the drive frequency. But despite this kind of highly non-equilibrium distribution, if I then allow the system to evolve unitarily under its own Hamiltonian here, then you see that local observables fairly quickly reach some kind of steady state, which agrees almost perfectly with the prediction of the microcanonical ensemble of statistical mechanics, okay? And so this is what we mean by pure state thermalization. So this plot here shows a comparison between the points, which are the kind of time average long time expectation values of this local observable, against the blue line, which is the prediction of the microcanonical ensemble, with a temperature that's just determined by the average energy of this initial preparation, okay? So here the temperature is really defined in a kind of classical way. The inverse temperature is the derivative of the entropy with respect to energy, and the entropy is the logarithm of the number of states in the microcanonical shell, okay? Okay, so this shows that we have thermalization of observables in this pure state, but this thermalization is even stronger than this, because we also have thermalization at the level of kind of 2-point correlation functions, okay? So if I look at a 2-point correlation function evaluated at some kind of long time after the system is equilibrated. So this observable A could be basically anything, but here I've chosen some particular choice. I mean, this is just some kind of smeared magnetization. The UJ are just some kind of coefficients. And so this correlation function has a real and an imaginary part, okay? And if I consider the Fourier transform of these two parts, then I find they're related by this fluctuation dissipation relation, okay, which is exactly what you'd expect for an equilibrium system, okay? Actually, if you compare the temperature that you would sort of infer by comparing these two parts and the microcanonical ensemble, you find that they agree almost perfectly, at least at sort of relatively high energies, okay? So this is all, of course, well understood. We are not the first people to show this by any means. It's been studied both theoretically and experimentally. And I would say in this particular system, we can fully understand where this behavior comes from through something called the Eigenstate thermalization hypothesis, which I'm going to just try and briefly explain in one slide. So the basic idea of eigenstate thermalization is that each individual energy eigenstate of our many-body system contains basically all of the information of the entire equilibrium ensemble, okay? And it's kind of can be formulated in terms of this ansatz for the matrix elements of some local observable. It could be any local observable, okay? The matrix elements of this observable in the energy eigenbasis, okay? And so what we have is a diagonal part and an off-diagonal part. So the diagonal matrix elements are given by some smooth function of energy, right? And that's actually sufficient to explain thermalization of observables, right? So this is kind of illustrated here, where I've plotted the diagonal matrix elements of some observable as a function of the energy density. And you see that with increasing system size, these diagonal matrix elements, they all concentrate around essentially just a single line. And this line is exactly the microcanonical prediction. So the reason why this is important is because it just tells you that you can pick any single one of these eigenstates, right? And you're going to get almost exactly the same thing as the microcanonical prediction, where you average over many of them, okay? And this, I mean, you can show that this is sufficient to explain why we see this kind of nice thermalization in time of these observables, starting from some non-equilibrium state psi, okay? And then crucially for this talk, there's this off-diagonal part of the ETH ansatz, okay? So this part here describes the off-diagonal matrix elements, okay? So we have some factor, which basically is an exponential suppression factor. So S is the entropy that I showed you on the previous slide, okay? Then we have some, I mean, basically some smooth function, okay, which is a function of the average energy, which is essentially related to the temperature, and this frequency, which is related to kind of the oscillation frequency of the corresponding coherence, okay? And then finally, we have these kind of pseudo-random numbers, which just have some zero mean and unit variance. So basically what this is saying is that the off-diagonal matrix elements, they're exponentially small, okay? They're erratically varying. So this actually shows you some examples of the off-diagonal matrix elements. So you have this huge cloud of erratically varying points that are exponentially small, but underlying them is this kind of smooth function of frequency, okay? And this function here, you can see that actually at low frequencies, it's particularly sensitive to the temperature, okay? And that's going to be the key insight that forms the basis of our sort of thermometry scheme, okay? All right, so whistle-stop tour through kind of pure state thermalization. I hope it's relatively clear. Now I'm going to move on to how we can actually measure the temperature of these pure states, okay, using interference. All right, so our idea is to use this kind of idea of thermometry by decoherence, okay? So imagine that our thermometer is now some two-level system which we place in contact with our kind of with our many-body system. This thermometer has two states, and what we do is we prepare a superposition state, we allow it to evolve, and then we measure. And you can think about this procedure as sort of by analogy to an optical interferometer, where the two states of the qubit are the two arms of the interferometer, okay? And of course, because it's quantum mechanics, we have the freedom to measure in many different bases. So if we map out the detection probability as a function of this kind of measurement angle on the Bloch sphere, then you see that you'll get this kind of interference pattern with peaks and troughs of kind of probabilities, okay? So this is just showing what a histogram would build up after many measurements. Okay, so now to measure something of the environment of this qubit, we assume that it's one of its energy levels has an energy that depends on some property of the environment, this A of T, okay? And this is going to introduce a phase shift into one arm of the interferometer, okay? And a phase shift in terms of the interference pattern, it just shifts it along the screen, okay? So that's just what I'm showing you here. You get a phase shift. And this is depending on some property of the environment. And so if the environment is thermal, then thermal fluctuations will lead to a kind of fluctuations in this phase. And you can imagine that your interference pattern is then going to be washed out. And so by measuring how this interference pattern gets washed out in time, you can infer the temperature, right? So the higher the temperature, roughly speaking, the faster your kind of thermal fluctuations will lead to decoherence, okay? And so this idea of kind of thermometry by decoherence has been proposed before. We're not the first people to do this, but pretty much all of these kind of works have assumed that one has essentially some canonical state underlying. Okay, and so our contribution is to see how this plays out really for a generic system, which may be strongly interacting and maybe in a pure state. Okay, and I just want to mention also that this kind of interferometry experiments with a qubit embedded in a many-body system can be done in ultra-cold gases, and there's a couple of experimental references, beautiful experiments, so I recommend checking them out. Okay, so let me move on to the results. All right, so let's see. So I showed you a kind of very semi-classical description of this interference experiment where this A was just some fluctuating parameter. So if we want to be a bit more careful and write down the full quantum description, then we basically just have this A being actually some observable of our many-body system that we want to measure, and it couples to our qubit by this kind of Hamiltonian here, which leads to essentially a pure dephasing open systems problem. Okay, and so this problem can be solved exactly, at least formally speaking, okay? And one finds that this interference contrast, which is a measurable property of the qubit, just has this particular form here. You get this overlap of two different states. It's also called the Low-Schmidt echo for those of you who are familiar with this, okay? Okay, so to make progress, we need to make some kind of assumption. So we assume that we have some weak coupling, all right? And then we can do, basically, we get a result that's very similar to the intuition that I already showed you, which is that the decoherence sort of proceeds as a consequence of the fluctuations of this observable A, okay? But these fluctuations are now quantified by this correlation function in time, okay? And if I consider sort of relatively long times, then basically what I find is that quite generically, I'll find pure exponential decay with a decoherence rate, which basically is given by this zero frequency noise, okay? And this connects directly to this spectral function of ETH that I already mentioned before. And this is nice because very, very recent work has kind of shown that the low frequency behavior of the spectral function is really a kind of sensitive probe of quantum chaos, and it's generically finite, okay? So we can conclude from this that basically an arbitrary sort of quantum chaotic many-body system will always lead to Markovian decoherence of some embedded qubit, and I think that's quite nice. So you get this kind of ohmic behavior of your bath, but the bath is now not a sort of collection of non-interacting harmonic oscillators. It's a collection of strongly interacting degrees of freedom, perhaps even in a pure state. Okay, and so our numerics confirms this prediction. So you see that even for sort of moderate coupling of the qubit to the bath, you get this perfect exponential decay that agrees very well with the weak coupling prediction, and this decoherence rate contains quite a lot of information on temperature. So this kind of thermometry method makes sense. All right. So in the last kind of 30 seconds, I'll just conclude quickly. So, I mean, the basic idea of this talk is to introduce this idea of pure state thermometry, which is kind of cute because here everything is described by just unitarily evolving wave functions, and we get this temperature scale that's defined purely by quantum interference. Okay. And so, I mean, one of the pros of this, I mean, the pros are that this kind of works for generic systems because it's based on decoherence. It does not require fine-tuned energy levels, which is kind of nice. However, you do need sort of detailed knowledge of this decoherence rate in order to infer temperature. But we were able to derive some kind of general expressions based on hydrodynamics, which just depend on sort of a few macroscopic parameters. And I think this kind of opens up some interesting questions, such as, you know, how can we derive the ultimate precision bounds for states beyond the canonical ensemble? Okay, and so with that, I thank you for your attention. I thank my co-authors, my funders, and please do check out the archive for more details. Thanks.
Thanks, Mark, for the very nice and interesting talk. Are there questions? In the meantime, maybe I can ask one. So yeah. You just argued, right, that in this quite very generically, you get to this ohmic distribution, right? Mm-hmm. Independently of the Hamiltonian that we have. Mm-hmm. So what then, when people have sub-ohmic or super-ohmic bath, is just an invention, or there are places that you could microscopically find something like this?
So I think you need our understanding of this is that you need an integrable system. I mean, okay, subohmic baths, this is a whole different story, right? I mean, so I think the question of how to get a subohmic bath, even from a collection of harmonic oscillators is somewhat a bit tricky, right? But I mean, for superohmic, typically, right, when one writes down the standard, spectral density, the standard open systems model with kind of non-interacting bosons as your bath. I mean, most spectral densities, right, most power laws are going to be superohmic. I mean, because you just have some power law, and I mean, unless it's exactly omega to the power 1, then you basically are going to have superohmic behavior, right? Omega squared, omega to the cube. And these kind of things generically come about when you consider like phonons in 2 or 3 dimensions and so on, right? So they are natural, but they are kind of a property of integrable systems, I would say. I mean, so we expect that, I mean, this translates in this language to a kind of a noise spectrum that goes to 0 at 0 frequency. And we know that this is generically the case for integrable systems. So in an integrable system, you should expect a highly non-Markovian behavior. In a chaotic system, you expect Markovian behavior. That's just somehow the conclusion of this work, which I think is kind of intuitive.
Okay, yeah. Well, that's very interesting. I would have more questions, but wait, sure. I saw a raised hand, but maybe.
Me, but Mark answered my question at the end of his comment to you, so never mind.
Okay, good.
Okay, thank you. So, are there other questions? I don't see any in the chat.
Maybe I can ask a question.
Sure. Hi.
Okay, so thanks a lot. Hi, thanks a lot for the very nice talk. Okay, so a very naive question. Mm-hmm. So your system, your probe is locally interacting with one of, let's say, one part of the actual big system that you have. Mm-hmm. So I guess one way could also be like to look at the reduced state of this local part and see. I guess the reduced state also has some information about the spectral density and so on. Is it enough to do that, to only look at that, or the correlations with the other parts of the bath are also playing some role here?
No, I mean, this is a very good point, right? So, I mean, and indeed, so any observable in a thermalizing system is a thermometer in principle, right? As long as you understand what the parametric temperature dependence is, right? So absolutely. I mean, if you can just do some local measure, I mean, I even showed you this now. Let me see if I can go back. I mean, you know, if assuming that you understand very well the this temperature dependence curve, right? Okay, then just by measuring a local observable of your many-body system, you can also infer temperature. And likewise, you know, if you can also do traditional thermometry here, right? You could plunge, you know, some thermalizing qubit into your bath, allow it to exchange energy, and by that way also kind of infer the temperature. So all of these things do kind of work. I mean, the main, let's say, contribution here is just to show that this actually makes sense for really these pure states, and to show, I think the nice thing about the decoherence is, apart from the kind of advantages and disadvantages that are well known of this method, that you really get some temperature scale purely from a kind of a pure state just evolving unitarily. But I think for me, the more interesting question for thermometry is kind of still unsolved, which is, you know, what are the ultimate bounds on thermometry for these states that are not actually given by a canonical ensemble? I mean, is it different for a microcanonical ensemble? Is it different for really a pure state? This is kind of open, I think.